Hi everyone and welcome back to this channel. In today's video we will enjoy one of the most satisfying aspects about the data analysis or science world. I'm talking about the 3D plots. I gotta admit that when I was still doing financial modeling in Matplotlib time ago, I was so obsessed with the surface plots that I ended up switching my career to data analysis step by step. It's sad but true. So if your secret dream is to leave a flat land once and for all, that's the video for you. The good news is that you can easily follow and learn it from the Matplotlib's official documentation. In my opinion, it's really easily to follow and beginners friendly. And with Halloween approaching, I chose a coherent theme for my Visual Studio code. For those interested, it's this one here, All Hallows EV+. But now, without further ado, let's jump into the code. Okay, first of all, we need to import the necessary libraries. Likely, we only need a couple of them. Matplotlib for the plots, of course, and NumPy for handling all the arrays. Well, actually there will be another line to add, but you will see it in short. Okay, now let's just see the basic grammar for creating the 3D plots. I'll show you two ways. In the first one, we'll use it plt.axis and projection 3D. That's probably the most common. But however, I prefer another command that allows me more flexibility. That's plt.figure and projection 3D once again. Add subplots. Once you run it, you will notice that it now displays a sort of cage with 3 dimensions, even if we didn't provide any input data. However, we can't do anything with it. It's pretty static, and I want it dynamic. We can do it by adding another line of code at the beginning of it. However, this command will change according to your work environment. If you use a normal .py file, you need to add from mpl_toolkits point and plot 3D and axis 3D. Otherwise, for a Jupyter kernel like this file, we need to write the magic command %matplotlib widget. Pay attention, no matplotlib notebook, but widget. Now, if we run it again, we'll see an evident change. I'm able to interact with my plot. I can rotate it and I can zoom it. So I'm finally ready to feed my plot with my variables. Let's start with an X array. Now, to match the same number of elements of the X array without making any math, we'd better know its shape. Perfect. Now I know I need 40 elements. So this time I will use random.randint just for showing you that several commands can be used together, as long as correctly put into the same shape. And here we are. We have made a 3D plot with only 2 dimensions. In fact, when rotating, you will find out that all elements are at the very same height. Just let me replicate it with some points in a scatter plot. Okay, I like it, but I feel like I miss some depth. Come on, I really crave the fifth dimension. So, let's see now how to add it. Actually, adding the third dimension, it's a pretty straightforward process. We only need to add another variable, as usual, the z, and generally it must be used as a function of the other two arrays. So in this case, I just sum up the square of the two variables. Once I've done it, I just add it into my scalar, and I'm ready to run it again. Now from the plot, you will see that the plot has changed something. Each point has a different height, and that's what I was achieving. But I suggest you to customize your plot with the colors. That's for many reasons. The first thing to do is to bear in mind that the C, for color, must be used as an array in this case, and I select X so that I will not raise any errors. Then I just select a C map, a color map, as I wish, in this case plasma. Run it and you see that we have the same plot, but just a bit bad, good looking, okay? Now we're ready for the next step. I think it's worth to spend a few minutes before moving on to the other kind of charts to explain these two inputs that are often misunderstood by people, and we will lead to a series of problems. We will see it by making a very stupid example. I'm talking about ZS and ZDIR, which are two of the most important inputs that allows us to customize our data inside a 3D plot, even if we were plotting a 2D chart. Let's see immediately an example. Imagine I'm working for a data analysis company or marketing company, and I want to work on a survey that has been made to a series of people. These people coming from 20 different countries, and for each of these countries we made a sample of people which have been divided, or 20 people each, which have been divided into 4 categories according to their age threshold. Now, let's start, first of all, to define our arrays and our variables. The first one means all the values which have to be displayed into bar charts. So, a random of 20 people, which may come to one of the 4 bins. In this case, I have to select 5 because 5 is excluded. So 20 people for each of the countries will be tested to a survey. And these people will be broken down into 4 categories according to their age threshold. Now I explain the NumPy arrange. Once again, I want 20 elements, so from 1 to 21. And with this interval. And finally, I can just have to do the same thing we did before. So AX equals PLT figure, add the subplot, projection 3D. In this case, I'm able now to plot a bar chart with X and Y. If I don't add anything else, this is what I got. Unlikely what we were expecting, we've seen a very anonymous chart with only 4 bins. Even if we say 20 countries, and for each country a survey of 20 people, divided into 4 age. This one X, the bins of my age threshold, and this one are each of the countries they come from. I don't like it. So what happens, first of all, if I change the direction of the height? Look at here, in fact. All the elements are on the 5th dimension at the same height of 0, because that's the default. This position, according to the Z dimension, it's called ZS. It may be a number or an array. In this case, I want to change it to x. If I change to x, now I got 4 different bins as once again, but all the height are referred to the specific bins of their age threshold. Unfortunately, once again, I only have 401 for all the 20 countries, and this is not what I'm looking for. My boss asked me to specify my data or to focus on the European market. So in my survey, I only have this data to add. Norway, Malta, Estonia, and Wales. The threshold age are this one. Remember, whenever you use a bar chart, you have to change the x labels to num and number plus 1. And these are the colors associated to each of this country or from Europe. Now, let me copy and paste this one on my chart, and let's see how to change the stuff. Now, first of all, let me show you the ZDIR. Now, you see that my plots display all the charts, all the bins, horizontally to the ground, parallel to the ground. I want to change it, and I say, instead of the x-axis, I want the y-axis. Now I got still 4, which is not correct, because I need to change the value. Now, I have, for each country, my sample for each of the 4 thresholds, but it's confusing. And my boss asked me to specify only European market. In this case, for doing that, I specify these things here. Plane. These are the plane where I will need to work on the y-axis. The points are 2, 4, 6, 8. So the position of my 4 European countries inside the 20 NumPy range. And this is what I want to show. Unfortunately, it will become an error if I make a plane. It cannot handle it. So now, how to do that? By opening a for loop where each color is associated to a specific plane. I'm showing you here the whole code now. Once I got the same information I plotted before, now I open a zip plane and color. So for each position, 2, 4, 6, 8, I got them, which are associated to Norway, Malta, Estonia, Wales. I got this specific color. And then I do exactly the same in this for loop. The only thing which changes now are ZS and color. ZDIR is always Y. ZS now become the specific lane, let's call this way, lane, of each of the position of my small plane list. And the color, it's the one associated to that country. Nothing more, nothing else. If I run this code now, this is what happens. Apart from all the name or the labels, now I got red for Norway at this position, Malta, Estonia, and Wales. As my numbers has been just a random number because I didn't make any test, of course, any survey, we'll see that now I got some insights about how people drink according to their age in Norway. Between 16 and 30, they were supposed to be not a real big consumer of alcohol, and more when they get older. Okay, don't pay attention to this insight now. But however, this is just an example to make you understand how to use these 2 words, these 2 inputs, even for the future, for other kinds of data, because that, as I show you now, they provide you more insights according to customizable information. For plotting surfaces, wireframes, and other 3D plots, we need to understand what Meshgrid does, because Meshgrid is the necessary step for plotting this one. Otherwise, they cannot have this plot by using the same procedure as we've seen before. Start by defining our arrays, like to NumPy arrange between -5, 5, and interval of 0.1. And now, let's see how they look like. Prints. Both X and X shape. That's the starting point for understanding everything. we see that we got an array of just 100 elements that you can understand by this single square bracket. However, if I now create a third variable like z in this form, it cannot allow me to plot a surface and a wireframe, because z in this way will just be an array or a single array like x and y. On the other hand, for the surface and a wireframe, I need a matrix given by the number of x times y. Okay, and that's what the Meshgrid does. I get x2 and y2 as a result of a numpy Meshgrid of x and y. Now, if I plot x2 and x2 shape, you see I got a double square bracket, so a matrix of 100 times 100. Now I can plot a Meshgrid, and so now I can plot a surface and wireframe. So z it's now a function numpy sine of x2 plus numpy cosine y2. Okay. Okay, and finally dot plot surface, or you can even choose plot wireframes in this case of x2, y2 and z. This is what I got. Okay, yeah, add subplot, and this is the plot I got. Now that you know how a Meshgrid works, and now a surface, by the way, let me show you even a wireframe, just to make you understand the difference. But now, let's see what happens if I add, for both wireframe or subplot or surface, a row stride, for instance 10 r stride, and c stride equal 10. First of all, what does it mean here? Let's say 30. C stride and R stride are referred to row stride and column stride of my F or my Z X2 Y2 structure of the matrix. So now I'm just reducing the number of my sample, downsampling, to a number that I decide. The higher is the number, the smaller will be the sampling, so the smaller will be the number of my frames. And that's how they look like. You see? But it doesn't take to do just a wireframe, even a surface. And that's it. Now, if you want to see the difference between the two, in the first plot, we see just the surface as it is. And the second one, I just reduce the number of the frames. And that's how they look like. You see the interval of the values, it's always the same. But now, my square, my frames, my mesh, however you want to call them, are bigger and in a smaller number. Because if you zoom here, you see a higher number of frames of a smaller size, compared, of course, to this one. And that's how a Meshgrid works, and how R stride and C stride works for this kind of plots. Before ending this video, I'd like to show you a couple of examples taken from the real data science/modeling world, where surface plots are used. The first example is taken from my past financial background, and it displays the surface plot from the Black and Scholes formula. In short, the Black and Scholes formula is the most popular way to compute the fair price of an option. An option is a derivative of financial instrument that gives the owner the right to buy or sell an underlying asset at a specific price in the future. An underlying asset can be, for instance, a Tesla stock. Relax, I'm not going deep. I just want to show you that this price is derived by a series of explanatory variables, as we see. In the plot I'm showing you now, the option price is the Z variable, while X and Y are the underlying price, the Tesla stock, and its volatility or risk. By rotating the axis, you will see how price starts skyrocketing after a specific threshold. In this case it's 100 or a bit less. That's the exercise price, so the price I decide to buy. The point where I start getting money from my call option, in short. What is important for a modeler here is that you can replace the two axes with other couples of variables. For instance, time to maturity, exercise price, and so on. In the real world, these variables gave birth to the so-called Greeks. And not these Greeks, but those parameters that show how the option price change according to a small change over all these variables. Anyway, the second code is by far the most known about the data scientists. I'm talking about the gradient descent. Long story short, we're talking about a great algorithm to compute the optimal values for a function, known as the cost function. That's in order to reduce the error of a supervised model. This minimal error that we're pushing it is the local point of minimum you see in this simplified plot. X and Y are the two arrays as usual, while my Z values come from a function of the two. The series of red points you see are the derivative points of the function, or the path. Great! Now you know that 3D plots are not just cool for your eyes, but very efficient instruments to detect insights from the real cases and analyses from the real world. That's all for today. I hope you enjoyed this video and the contents I created. If you did, please consider to subscribe, like or comment and share this video. Okay? Bye bye and see you next time.